непористий 3D кремній,
3D silicon, high-performance electrode nanomaterial for new generation lithium-ion batteries. Sergey Kuksenko, please, welcome.
The subject of my report is non-porous three-dimensional silicon as electrode nanomaterial for new generation lithium-ion batteries. Manufacturing technology of lithium-ion batteries is very simple, so it took a bit of time from invention, 1985, to large-scale production, 1991. In 2012 alone, more than 12 billion lithium-ion batteries were produced. And this figure sharply increased. The market of lithium-ion batteries moves from the small scale applications to the large capacity sectors, including large-scale electric vehicles and energy storage systems. The predicted market expansion of lithium-ion batteries from 2010 to 2020 is surprising, with a tenfold growth from more than 11 to 119 billion United States dollar, considering that the market growth driven by lithium-ion batteries for mobile devices between 2000 and 2010 was said to be exploded, with only the figures from more than 5 to more than 11 billion United States dollars. The mobile device sector of the market is predicted to expand only 2 times from 2010 to 2020, which is the same growth rate in the former decade. More than 80% of lithium-ion batteries market at 2020 is predicted to be occupied by 2 emerging application sectors. Those are energy storage systems and electric vehicles. Energy storage system sectors weighs about 44% of the total market size at 2020. Lithium-ion batteries consist of 2 electrodes in form of the thin layers on the copper and aluminum foils, and wet aprotic electrolyte separator between them. The main cell reactions in lithium-ion batteries are reversible lithium-ion incorporation extraction between in charge-discharge cycles between 2 insertion compounds. The positive electrode in current lithium-ion batteries typically consist of lithium 3D metal oxide or phosphate as active material. On the anode side, most lithium-ion battery cells use graphite-based active materials. With such a simple technology, a problem of large-scale production rests not in technology but in science. In recent years, the interest in the research and development of new active materials for the anode and cathode in lithium-ion batteries has been increased significantly. Electrode materials will play a major role in the next generation battery design. According to Navigant Research, the primary component materials from lithium-ion batteries are expected to increase from more than $7 billion market in 2014 into a 19 billion market in 2023. As promising materials from the positive electrodes, considered stable in air lithiated layered oxides, fluorophosphates, silicates, and structurally integrated composites. Interesting candidates as new active materials on the anode are typically metals or semi-metals, which are able to electrochemically and reversibly form alloys with lithium. These materials exhibit very high theoretical rechargeable capacities due to the higher amount of lithium which can be reversibly stored in alloys compared to the carbonaceous or graphite-like carbons which exhibit an intercalation-based storage mechanism. For example, readily available and cheap silicon is able to store 3.75 lithium atoms per atom silicon in the form of the following composition: lithium-15, silicon-4. The higher amount of lithium that can be reversibly stored leads to a significantly increased theoretical gravimetric capacity of silicon with 3,579 mAh per gram compared to 372 mAh per gram for graphite, which is able to store 1 lithium atom per 6 atoms of carbon. The more drawback of silicon-based anode materials is the high volume expansion taking place during the lithiation and delithiation process, which can be up to 280% compared to the original volume. These volumetric changes can lead to several degradation processes. Examples: strong mechanic strains, pulverization, loss of electric contact between the different anode components, and to the failure in the stability and structure of anode electrolyte interface. To improve the structural stability of the electrodes around the silicon particles, usually create a space that is filled up with swelling alloy. Such strategy does not seem promising for practical use because of low loading capacity of the suggested electrodes and low coulombic efficiencies of the cycles due to renewing contact of the active surface of the swelling lithium-silicon alloy with electrolyte. For the first time, as a key characteristic parameter for rapid assessment of usefulness developed electrode materials and electrolytes for lithium-ion batteries, we propose to use the value of the irreversible capacity accumulated in N cycles, which is an integral indicator of irreversible binding of lithium ions in the electrode surface and in its bulk in N cycles. Identified the principal role of a natural oxide layer with the silanol groups on the silicon surface and the mechanism of reactions with its participation in the formation of passivation layer. In addition, we were the first to use a fluoroethylene carbonate-based electrolytes instead of ethylene carbonate. Ethylene carbonate was totally replaced by fluoroethylene carbonate. A new composition of a protic electrolyte was proposed with the introduction of 2 rather than the traditional 1 functional additives. Such composition of electrolyte dramatically improved the cycling parameters of alloying electrodes. After the appearance of our applications in 2010 devoted to the effectiveness of electrolytes based on fluoroethylene carbonate, a complete replacement of the ethylene carbonate on the fluoroethylene carbonate, the necessity in fluorocarbonate on the market has increased dramatically. With the aim to reach the acceptable values of accumulated reversible capacity at high capacity loading, we propose a new nanocomposite configuration, non-porous 3D silicon, wherein the silicon particles and graphene layers interconnected together through amorphous silicon oxycarbide, which gives them mechanical strength. Such structure is highly conducting and electrochemically active with respect to incorporation and release of large amounts of lithium. With this new nanomaterial, it is possible to control the strain of the lithium-silicon alloy, thus preventing its contact with electrolyte, and to fabricate high-density silicon-containing electrodes. The 3D silicon electrode cycling parameters achieved loading capacity more than tripled compared to graphite anodes, and accumulated reversible capacity equals only a quarter of reversible capacity, are due to high density of the electrodes and formation of stable interface electrode-electrolyte. Nano and sub-micro powders of silicon, or cheap micropowders of porous silicon or silicon monoxide, and polysiloxanes to be used for the synthesis of non-porous 3D silicon. The unique frame-ordered structure of the material has significant advantages. A ceramic frame serves as a conductor of electrons, fully protects primary particles from contact with electrolyte, allows lithium silicon alloy expanding without any change in the size of the secondary particles, preserves a high active surface of the primary silicon, and provides a high density of the secondary 3D silicon. Exceptionally high electrochemical parameters of the electrodes with non-porous 3D silicon is the result of the formation of stable interface electrode-electrolyte. The first time, the unique role of carbon in the stabilization of solid solution at the interface and preventing the emergence of crystalline phase was identified. It was shown that the amorphous phase improves the dynamic mechanical properties of the composites, facilitating sharp decrease in the accumulated reversible capacity of the silicon electrode and persistence increase in the retention of reversible capacity. Developed by us novel silicon anode materials and electrolytes for lithium-ion batteries provide an opportunity to sharp increase the energy density up to 400 watt-hour per kilogram, to lower the cost up to $125 per kilowatt-hour, and increase the surface life up to 20 years. Here are our publications in English. Thank you for your attention.
Thanks. Please, have any questions? My question, very short, is: have you any contacts with plant in Dnepropetrovsk?
No, any contacts.
Up to now, no.
Absolutely.
Another questions or short comments?
Or the Russian publications. In 1990s, we worked intensely with the Russian Federation, organized the production facility in Russia that functioned until the electronic industry collapsed. So we have a good cooperation, connections with Russia. Any other questions? Thank you, Sergey.